think 27. That's a good number. I hope you had a Merry Christmas and a very Happy New Year. Mine was a bit challenging. I got a bit sick, but I'm improving and I thank God. So when I was looking at the last lesson we had on the antibacterial agents, I realized we don't have much. Just 1 minute. So I actually realized we have almost completed on the on the sulfonamides, and we have only about 3 or 4 slides, which we'll look at this morning and finish, and then work on the lincosamides. So we should be able to finish today. God being our helper. I'm still a bit weak, but I'll try the best I can to see whether we can finish today. So the last lesson, and I hope I checked properly. I realized we had already looked at, or we had already compared the structure and size of the sulfonamides and para-aminobenzoic acid. And of course, the need for this comparison is because these two molecules are competing for the same receptor. They are competing for the same receptor, and of course, the receptor or the enzyme is dihydrooctanoate synthetase or dihydrofolic synthetase. And because they are competing for the same receptor, they must have structural resemblance, so that when they come to fit on the receptor, or when it comes to the affinity for the receptor, they will have a very similar affinity, very similar ability to bind the receptor. But now when they bind, one definitely will trigger a reaction, whereas the other will inhibit. Is the difference. So you might find the sulfonamide will bind a little bit more strongly, will prevent the para-aminobenzoic acid, but the sulfonamide cannot be converted to the folic acid because it is an antimetabolite. So the minute it binds, it prevents the correct metabolite, which is para-aminobenzoic acid, from binding. Once it prevents para-aminobenzoic acid from binding and itself cannot propagate the process of synthesis of the folic acid, that means that process is halted, inhibited, and that is the mode of action of those drugs. And therefore, for these drugs to compete effectively for the same receptor, they must have some structural resemblances. Of course, also they must have some slight structural differences, so that when one binds, definitely it binds and of course does not trigger pharmacological or any biological activity. And therefore, we had said when we look at the size of both para-aminobenzoic acid and the sulfonilamide molecule, you find that they are basically the same size. The difference is very simple, small. And we had said nearly of identical length, 6.7 angstrom for PAMBA versus 6.9 angstrom for the sulfonilamide moiety. So that again makes not allow the enzyme or the receptor to be able to differentiate these two molecules, either of this molecule, as long as it gets and bind the receptor. They are also roughly flat, and they are roughly flat because both of them do contain the benzene ring. When you have the benzene ring, these groups that are binding or joining the benzene ring will join, so that the molecule is actually planar. So roughly flat, have an equal distribution of charge, and we discussed this when we look at the amino group. And also we looked at the carboxylate group. We did mention that they do have an almost equal distribution of their charges. And because of the equal distribution of their charges, that means when that charged area goes to bind to the receptor, again, the binding will be very similar, both at the amino group, and they have the anilino moiety for both of them. So that area will carry the same charge. And then also the one has the carboxylic group, the other has the sulfone moiety, or the sulfonoyl moiety, or sulfonamide moiety, and the two are actually comparable. This effect can be seen more clearly by examining the electrostatic potential surfaces of these molecules, and that's what we have looked at, that because of the structural similarity, when it comes to the hydrophobic area, which is a benzene ring, that will bind both of either of the molecule will interact with the receptor through hydrophobic bonds. When it comes to the amino group, if the amino group is protonated, let's say for instance, amino group could be protonated at physiological pH, it will still give us the same interaction, even if it is not. The sizes are the same. Amino group on this side and amino group on that side does not make a difference. So again, the primary RNA amine is the same, again having the same interaction. And of course, we did mention this will be ionized to give us a carboxylate ion, and therefore giving us a polar, allowing us to have polar hydrogen bonding, and therefore this molecule, because of the structural similarity, it will have similar interactions with the receptor. And that is what we said at the next point. And we looked at the para-aminobenzoic acid, and you can see that is the amino group there, and that amino group, which has a nitrogen attached to a hydrogen, can interact with the receptor very effectively for both para-aminobenzoic acid and even for the drug. And that is why we say this group cannot be substituted, because if you substitute and you do not have a free amino group, then you introduce steric hydrogens, you will block that binding through hydrogen binding and therefore interfere with the activity. So as I have said, that area through hydrophobic bonds, or what you call van der Waals forces, and that area is the same in both para-aminobenzoic acid and even the drug. And then, of course, the final area where you have the carboxylate ion, which definitely will be the carboxylic group will be ionized at physiological pH to give us the anionic center, and it will interact through electrostatic bonding or through what we are calling ionic bonding. And the same case here, we did mention that this group, through stabilization by resonance, we did discuss that, stabilized by resonance, and once it is stabilized by resonance, then this area very readily loses the hydrogen ion to give us the anionic charge, and therefore that center there, again very similar to the carboxylic center of para-aminobenzoic acid, and interact through the receptor via ionic bonds. And that's indeed the reason why we were saying when R is an electron withdrawing group, when R is a heterocyclic electron withdrawing group, that will stabilize, or that will give this drug more activity, higher potency, because there will be better formation. There will be more, the anionic group will be more ready. It will also be more stabilized when R has a heteroatom which has lone pairs of electrons. And the better the stabilization of this ion, the more stable, the higher the ionization of the sulfonamide, and the better its reactivity. Because we did mention it is the ionized moiety which brings about pharmacological or biological activity. So that comparison is very, very important, and it shows why the sulfonamide has to have a specific structure, to meet some structural requirements to be very closely related to para-aminobenzoic acid so that it can compete for the same receptor. This one we had mentioned, I don't know why it looks so big. I'll update this one now. That's what we had done. Mechanisms of microbial resistance. So I hope that that is clear, but that was even just a recap. We had already mentioned the structural resemblance between para-aminobenzoic acid and the sulfonamides. What are the mechanisms of microbial resistance of the microorganisms towards the sulfonamides? Of course, I did mention sulfonamides were some of the first antimicrobial agents to be developed, and they were considered to be like water drugs. And unfortunately, because of the way they were found to be very effective, of course, before then, there had not been much exposure of microorganisms to antibacterial agents. And therefore, when they were developed, they were highly effective because microorganisms had no resistance at all. But the danger is when they were discovered, they were misused. They were used for basically everything, even for infections for which they did not have activity. And because of that irrational drug use, definitely a lot of resistance developed. And indeed, as I have been like the sulphonamides, we don't use them anymore as anti-malarial agents. Even we don't even use them much for most of the bacterial infections because most of the bacteria, because of the irrational use, have developed resistance. So what are some of the ways in which they can develop resistance? We can see the indiscriminate use of the sulphonamides led to the emergence of resistant strains of bacteria, and resistance can be acquired through several ways. One of them, compensatory increase in biosynthesis of PAB. Remember, this blockade is what we call competitive inhibition. Competitive inhibition is concentration dependent. So if you increase the concentration of PABA, more of PABA will get to the enzyme than of the sulfonamide. Because again, you must remember, you must have you must control, you must have the minimum or the maximum dose with minimum toxicity. So if you increase the concentration of PABA, you cannot be able to also increase the concentration of the drug because of toxicity. And therefore, once you increase the concentration of PABA, then the PABA will be higher in concentration at the site of action, will still get to the receptor, and even in the presence of the sulfonamide, the microorganism will still synthesize folic acid. This is because it is a competitive inhibition. They are competing for the same receptor, and competitive inhibition is concentration dependent. The one which has a higher concentration at the site of action will more readily get to the receptor and bind the receptor and bring about its respective activity. Mutations at the dihydropteroid synthesis. We have looked at this severally, and you find sometimes the receptor, remember the dihydropteroid synthesis is the receptor, and just as we have said of all the enzymes, the transpeptidase enzyme, all of them, they can undergo mutation at the receptor site. Once they undergo mutation at the receptor site, then it means there will be conformational change on the receptor site, and the structure and the site will be different, and it will not be able to accommodate, it will not be able to be bound by the sulfonamide. But at times that happens, the mutation, but that mutation allows that enzyme to bind the original substrate, but not the anti-metabolite. So that can happen where you have mutations and resulting in conformational change, which does not allow for the binding of the anti-metabolite, the sulfonamide, but allows for the binding of the actual substrate, which is para-aminobenzoic acid. Decreased cell membrane permeability to sulfonamides. If there is decreased cell membrane permeability, it means the concentration within the cell or the microorganism will be low. It's competitive inhibition, and therefore that will render the sulfonamide not active, because it is not, again, that occur because of certain mutations, that the permeability of the membrane is decreased, little or very low concentration of the sulfonamide is getting into the microorganisms, therefore does not support competitive inhibition. Active efflux of sulfonamides, we have mentioned this even for tetracycline some time back. Usually, most of the mechanisms that accumulate these drugs in these microorganisms, again, is concentration gradient. You can have the concentration gradient of the drug in plasma is low, but it is still moving into the microorganism, because normally we use active transport. And that's what we're calling the active transport or influx mechanisms. Active transport, which is pushing the drug inside the microorganism. Now the microorganism again comes up with encodes for a different enzyme that pumps the drug out. And that's what we're calling the efflux. So as the drug comes in, it it's pumped out. As the drug is pumped out, again, that will not allow for competitive inhibition because the concentration of the sulfonamide will not even reach the minimum inhibitory concentration. Then acquisition of another copy of or DHPS through a plasmid transfection. The DHPS is a dihydrofolate synthetase. In other words, it is like the microorganism synthesizing a different type, slightly different. So it might change in one or two sequences of the amino acid, but the enzyme is to be able to bind the para-amino benzoic acid. So coming up with another copy of the dihydrofolate synthetase enzyme changes a little bit, or it is more than in microorganisms that do not have resistance, and therefore since enough of the dihydrofolate synthetase enzyme, even if you block some will still be available. So you have enough of the dihydrofolate synthetase enzyme. So even if you block some with the with the sulfonamide, you still have some left, which is enough to still bind the para-aminobenzoic acid. Again, this is effective because, as we said earlier, you cannot increase the concentration of the sulfonamide beyond certain concentrations, because if you increase the concentration of the sulfonamide beyond certain concentration, remember issues of crystalluria, remember issues of cytotoxicity, which we said does occur on metabolism. So the dosage of the sulfonamide must be the maximum with minimal toxicity, the maximum that you can give with minimal toxicity. Beyond that dosage, you cannot increase. Beyond that, you cannot the dosage of the sulfonamide because of the toxicity. So the microorganisms now make sure they synthesize a lot of the dihydrofolate synthetase, dihydropteroid synthetase enzyme, and therefore they have beaten, of course, they will have beaten us at our own game. So those are some of the 5 ways in which the microorganisms were able to acquire resistance towards the sulfonamides, and no wonder, as I have said now, because of the indiscriminate use, most of the sulfonamides are not being used. They're not being used, but we can still say sulfonamides are still being used in the management of HIV and AIDS, and of course other parasitic conditions. So synthesis of the so now we look at the synthesis, and we look at, first of all, the synthesis of sulfanilamide. We did mention sulfanilamide is the prototype. It is the prototype. It is the simplest. It's a 4-aminobenzene sulfonamide, and we can start the synthesis of sulfanilamide using benzene. I think in your first year, second year, you did cover aromatic electrophilic substitution. I think that is taught either in first or second year in organic chemistry. That's organic chemistry. So aromatic electrophilic substitution. And I believe you mentioned quite a number of reactions where benzene can react with an electrophile. So you bring in an electrophile, considering that because benzene has some delocalized electrons, that density, those delocalized electrons, which are not bound anywhere, they are moving freely, can be available to react with an electrophile, and that's what we are saying, an aromatic electrophilic substitution, and whereby you are able to substitute one of the hydrogens in benzene with an electrophile. Then the electrophile must be a molecule that is electron deficient. So molecule which is electron deficient, and once you bring in a molecule which is electron deficient, it is coming to replace the hydrogen in that kind of reaction we are talking about, aromatic electrophilic substitution, as I have said, which you must have done in first year. So with the first move, when we want to make the sulfonamide, is to put a nitro group, and this is the reaction that is aromatic electrophilic substitution, which we call nitration. So the first step here is And when you do nitration, you use nitric acid, but nitric acid is a very weak electrophile. So it's a very weak electrophile, and even benzene is quite a weak nucleophile. So if you bring a weak electrophile and a weak nucleophile, the rate of reaction or speed of reaction is so low that it might take forever for that reaction to happen. So you add sulfuric acid, concentrated sulfuric acid. So that nitration occurs in the presence of nitric acid, in the presence of sulfuric acid, and that's what we're calling nitration. And it's an aromatic electrophilic substitution. The nitro group is being generated from the nitric acid and the sulfuric acid. So you generate NO2 positive. And that NO2 positive is our electrophile, and it is the one which will replace one of the hydrogens of benzene. And then after you have done that, you hit the nitrobenzene in the presence of sulfuric acid. You hit it in the presence of sulfuric acid, and you get a substitution, and we can call this nitrobenzene sulfonic acid. So you're only again replacing. So this now is sulfonation. So we are replacing one of the hydrogens with sulfonic acid. So you get nitrobenzene sulfonic acid, and then you react that with pentachloride. You can see that's pentachloride, and once you react it with pentachloride, it gives you nitrobenzene sulfonyl chloride. All you have done is that you have replaced a hydroxyl group, because this was SO3H, so you must have removed H group and replaced it with a chloride group. So that we can call nitrobenzene sulfonyl chloride. And then now, after you have gotten your nitrobenzene sulfonyl chloride, you react it, you reduce it. This is a reduction reaction using tin in hydrochloric acid. That's a very good reducing agent, and it will give us the para-amino, to give us para-amino sulfur. I think I can call this para-amino sulfonyl chloride, para-amino sulfonyl chloride, to give us that para-amino sulfonyl chloride. And then after that, you react it with concentrated ammonium hydroxide, and you get your sulfanilamide. You get your sulfanilamide. I think I went to the second one. Yeah, I think this is the first one. Yeah, from benzene, that's okay. So then you get your sulfanilamide. So again, the first one is a nitration, an aromatic electrophilic substance to give us nitrobenzene, and then you do sulfonation by reacting with sulfuric acid, and you hit, it gives you nitrobenzene sulfonic acid, react with phosphorus pentachloride, just to replace, to give us the sulfonyl chloride. Whenever you have a chloride moiety substituted on a molecule, chloride moiety is kind of active with reactions. So you put your chloride molecule there, and then now you do your reduction using tin in hydrochloric acid, react with ammonium hydroxide, and you have gotten your sulfanilamide. And definitely sulfanilamide can be used as a lead molecule. It can be used as a lead molecule in the synthesis of many other sulfonamides, as long as, of course, many other sulfonamides, just as we talked when we were discussing, of course, I think in third year, when we were discussing something like 6-amino penicillinic acid, 7-amino cephalosporanic acid being used as lead molecules, and you start there and you do the relevant substitution, and you'll be able to get whatever drug you want. So this, considering that it has an amino group there, it also has an amino group there, so it has this hydrogen available for replacement. So therefore, you can replace one of these hydrogens with different moieties depending on which sulfonamide you want to synthesize. So it is important first for you to be able to synthesize your sulfanilamide, and then the sulfanilamide will act as a lead molecule for the synthesis of several sulfonamides. Then the route 2, so that was the route 1, and the route 1, we started with benzene. So the route 2 we want to start. The route 2 we want to start with nitrobenzene. So sometimes you can also start with the nitrobenzene. This is just sulfuric acid, which has been substituted with a chloro group. So we can call this chlorosulfuric acid. Chlorosulfuric acid, react your nitrobenzene with chlorosulfuric acid, and that means if you look at this, we have just gotten where we were So that's where we were here. So it's only that now we didn't use this method. We didn't start with benzene, we started with nitrobenzene, and we didn't react with sulfuric acid, we reacted with chlorosulfuric acid. Chlorosulfuric acid should be more reactive than the sulfuric acid. And all so, and of course, this we have added, we did not add the sulfonic acid, we added the sulfonyl chloride direct. So we missed one step there by using sulfuric acid, and then after that, the story will be the same. You react with tinin hydrochloric acid as a reducing agent, and then of course, as we had said, we react with ammonium hydroxide with loss of hydrogen chloride, and it gives you sulfanilamide. Now, once we have our sulfanilamide, as we've already said, you can synthesize other drugs. Like you can synthesize sulfacetamide. Remember, we did mention sulfacetamide is a good drug which has been used for quite some time for conjunctivitis, all eye infections. It is used locally for eye infections, and of course, sulfacetamide. If you remember, we said it is where on the terminal nitrogen you put an acetyl group. So you can do that by using acetic anhydride. This is CH3CO2, this is acetic anhydride. And once you do it using acetic anhydride with loss of a water molecule, then both amino groups are acetylated. The 1 and 4 amino groups are acetylated, and then you do what we call partial hydrolysis, and you are able to get your sulfacetamide. So of importance, this is just to demonstrate the need for the synthesis of sulfanilamide, because sulfanilamide can be used as a starting. Then another example is sulfamethoxazole, which we have mentioned that sulfamethoxazole in combination with trimethoprim is what you call cotrimoxazole. Cotrimoxazole is sulfamethoxazole in combination of trimethoprim. So very, very important, because as we had already mentioned, when you mix sulfamethoxazole plus trimethoprim acts on the tetrahydroreductase enzyme, the sulfamethoxazole act on the dihydroteroate synthetase enzyme, and of course we did mention sequential blockade. So you are blocking the same pathway for synthesis of folic acid, but at 2 different steps, and that is sequential. So you hit the same microorganism twice, and since you are hitting it 2 times at different positions, because at one point you are hitting the dihydrofolate synthetase enzyme, and the second step you are hitting the tetrahydrofolate reductase enzyme, you are able to actually change the sulfonamide from being bacteriostatic to being bactericidal. And that's what we did mention is sequential blockade. So here we can start with this compound here. So you can see this is isoxazole, carbamic acid. They're calling it isoxazole carbamic acid. And then you lose the carbon dioxide. And once you lose the carbon dioxide, then you get the 5-methyl isoxazole 3-amine. Again, you add this compound here, which we can call para-amino benzene sulfonyl chloride. Para-amino, we came across this the product when we were making the sulfanilamide. So para-amino benzene sulfonyl chloride. So you add that to this compound, and once you do so, then you find that this compound, because this is the group that we are adding, all of this group here. So you find that the whole of this group comes in. So you lose this chloro group. Chloro group is very easily lost here, because remember, the sulfonyl group is pulling away electrons. So this chloro group is a little bit naked, very, very easily replaceable. So all that is happening is that chloro group is being lost and being replaced on the amino group of the 5-methyl isoxazole amine. So this comes in, amino group comes there, and that's what you require, and that group there. And that way you are able to make yourself a methoxazole. Again, of importance is we have started with that. So even here we did not start with the sulfanilamide, but we started with one of the intermediates. We are using an intermediate which was there in the synthesis of of sulfonilamide. So that means you can actually, it means you can actually use, let's see, yes, you can go this step, so nitrobenzene and the chlorosulfonic acid, and you make that group that we are using, that is there. Then I think for this one, the other one, you will walk along a route, and this is the compound that we are talking about. So we are not using the sulfonilamide, but we are using one of the metabolites, or one of the products that was formed during the synthesis of sulfonilamide. So that, and you add your paramino benzene sulfonyl chloride, and you will get your sulfamethoxazole. So these are very simple methods of synthesis. That is why I'm explaining them. This one we looked at sulfacetamide from sulfonilamide. This is your acetic acid anhydride. This is how acetic acid anhydride looks like. When you see it written as CH3CO, is CH3C double bond O up to there, and then this. So CH3 C double bond O up to there, and they are usually two. CH3CO up to there, one, and then you have another one on this side. So they're usually two, CH3CO, CH3CO, then there are two on each side, and then an oxygen. That structure is acetic anhydride. You can have different types of anhydrides, but you require acetic anhydride because the sulfacetamide has the acetyl group. Like this. That one we looked at. So this again is just a repeat of what we have already looked at. And I think that is the end. I don't think I have anything else on the sulfonamides. That I think is what I had. So we have now covered the synthesis. We have covered ways of acquiring resistance. We have also covered similarities between sulfonamides and paraminobenzoic acid, which definitely is just a way of explaining the mode of action. And of course, that we have covered. I think that is all I had left for the sulfonamides. And I think now we are done with sulfonamides. So, unless if there is any question with your permission, I can go to the last topic.